Hello everyone. The intent of this presentation is to give a comprehensive understanding of Kotlin. Kotlin Kotlin makes software development easier. Here's a higher level list of improvements Kotlin has over earlier generation languages. We'll go through this list in detail at the end of the presentation. So let's jump into the basics. We'll start with data types. Like many programming languages, it supports some basic data types like int, float, boolean, string, arrays, and others. Quite similar to earlier generation languages like Java. Any, that's another data type, which is generally a base of all types in Kotlin. You see the similarity with object in Java. Nothing is another data type. There's no equivalent in Java. So when a function returns nothing, it means a function cannot return normally. It has to throw an exception to exit that function. Unit, very similar to void in Java. In Kotlin, nullable types are super types of actual types, as well as any. That is, string nullable is a parent of string, int nullable is a parent of int, any nullable is parent of any. In Java, a string, for example, can be assigned a null. Same with any class can be assigned a null. And hence, there's always a risk of null pointer exceptions. In Kotlin, however, since they are different types, nullable types are handled differently. And we will see that in the coming slides. Kotlin has support for classes similar to in Java, and we'll go through them in detail. In Kotlin, the object keyword is used to create a singleton object, very similar to static in Java. When you need classes to hold data, data class serves the purpose. You can declare all the properties in the primary constructor, and the compiler generates the rest of the boilerplate for you. So functions like equals, toString, copy, they're all generated by the compiler. Kotlin supports standard collections, which you have seen also in languages like Java, list, map, set. Here is a general inheritance diagram for collections. It shows list, set, and map. We will not go through them in detail, however, understand their type hierarchy. So let's take mutable list. Its supertype is list, which makes it immutable or read-only, which is itself a collection. Collections inherit from iterable. Kotlin has ranges to specify collections. So you can use a range expression to create a collection. The double dot is a way of specifying increasing order ranges. Kotlin also has syntax for decreasing order ranges as well as for custom step sizes. Along with collections, the Kotlin standard library contains another type, sequences. Unlike collections, sequences don't contain elements. They produce them while iterating over iterables. Here is a simple chain of operation on sequences. You have multiple intermediate operations. In this example, you see map and filter as intermediate operations called one after another. Intermediate operation returns another sequence, which is lazily produced. Sequence elements can be retrieved only after the terminal operations. In general, collections are eagerly evaluated. So after every intermediate operation, you get a copy of a collection. While sequences do so lazily. So unlike collections where a copy of the original collection is copied after the intermediate operation, entire chain of operation on sequences are iterated just once. And you may find it efficient to use sequences over collections directly for large data sets. Using sequences is a topic by itself and may need a more detailed discussion, not scoped in this discussion. Let's look at type declaration. This is very similar to Java. Val is similar to final, score is the name of the variable, and data type is long. The statement is a bit shuffled as compared to Java, but similar. General type declaration has four components. The first component is the mutability or declaration. In this case, val, which is immutable. You can either have a var instead of a val, which will specify that the variable is mutable. Variable name, in this example, it is called score. The data type in this example is long. And initial value in this example is 10. Let's understand our example a bit further. Declaration val marks the variable as score as immutable, very similar to final in Java. So if you try to assign a new value to score, obviously you'll get a compilation error. And if you see the difference here, variable 2 is a var, which means mutable. So it is perfectly legal to actually assign a new value to variable 2. Type inference. Let's compare the last line, greetings equals to hello, with the previous two examples, score or variable 2. You were specifying the data type very explicitly, long. In greetings, you're not specifying the data type. The compiler can infer from the initial value that the data type is string. So what you see here is an example of Kotlin can infer value of its type string, and hence it is not needed to be specified. So the general syntax for a statement would be you need the type declaration or mutability declaration, the name of the variable, and the initial value. If those are present, then the initial value can be inferred. Here are a few more examples. X is a long, temperature is a double, and greetings is a string. And based on their mutability declaration, val or var, they are immutable or mutable. And in the last example, score, it is redundant to specify long because the compiler can infer from the initial value that it's a long. Now let's explore optional types. Let's understand this statement a bit more. Notice the question mark after string. Notice the initial value is null. The data type needs to be explicitly specified. Kotlin cannot infer the type automatically because the initial value was null. Here is a general syntax for nullables. The data type needs to be specified. To understand optionals, we need a bit more discussion. Let's understand that in more detail. Let's take an example of a class, apple, which inherits from fruit and implements iEdible interface. Our expectation for this hierarchy will be as in the figure. Apple inherits from fruit and apple implements iEdible. As we earlier discussed, all types inherit from any, similar to object in Java. So we can expect fruit to inherit from any. In reality, the class hierarchy is a bit more complex. You see a mirror type hierarchy in the right with optionals or nullable types. Quite quite complex. Each type inherits from any as well as optional type, which includes any and any optional as well. So fruit inherits from any as well as from fruit optional, while fruit optional inherits from any optional. General parent-child type rules are then enforced. You can assign a child type to a parent and not the other way around. We can see that in a bit. This type hierarchy is the basis of enforcing null safety. Also note the multiple type inheritance is maintained by the compiler internally for the purpose of null safety and not explicitly supported as a syntax in the language. Before we jump into the details of functions, let's have some overview. Here is a general syntax of function variable. Function name on the left, comma separated parameters followed by an arrow, and then the function body on the right, all enclosed in braces. Notice the double colon prefix, prefixing the function if it is to be used as a value. Function signature as a data type. Notice the parameters are comma separated enclosed in parentheses. The return type is after the arrow. Functions can be nullable types as well. Let's take a closer look. We have two examples. The function name with the name Lambda is a very generic definition, comprising of a variable name, the function type, parameters, and then the function body. The function with the name add is very specific. It takes in two integer parameters and returns an integer. On the right hand side are the parameters in the body enclosed in braces. Let's look at class in Kotlin. Its declaration seems similar to Java, and we will use Java for comparison of class features. All classes are final by default and need to be declared open explicitly if you want them to be inherited. Notice the difference in syntax to extend a class. In Kotlin, we use a colon. In Java, all methods are open and hence overridable by default. In Kotlin, they are final by default. You need to be explicit in a method if a method needs to be open and overridable. See the difference here in Java, you annotate override. In Kotlin, it's a keyword. Kotlin class properties look similar to Java class members. Notice the difference in vocabulary. Properties in Kotlin versus members in Java. Also, val in Kotlin is like final in Java, immutable type. While var is immutable, in Java, immutable is default. You don't have to specify. There's no keyword assigned to it. In Kotlin, properties have hidden backing fields. The field itself can be accessed only by its getters and setters. There is no other access to the backing field. Java, the variable color itself is the field. While in Kotlin, color is just the property. Since properties are not member variables themselves, their getters and setters can be delegated to other implementations. Here is an example for cost. It is delegated to cost property. Let's see what it means. Notice the by keyword for delegation. All getters and setters to cost are delegated to the get value and set value of the cost property class implementation. Some examples of delegate are by lazy, by vetoable, by delegate. You can look for more details of each of the Kotlin of each of these delegates in the Kotlin documentation and the Android documentation for view model delegates specified in this slide. Access modifiers, they are very similar to what we see in Java. Public is similar to Java, visible everywhere. Private is similar to Java, visible inside class only. Protected is also similar to Java, visible inside class and subclasses. Here's the difference with Java. The internal modifier makes the type invisible, make the type visible inside same module only. Also notice, by default, Kotlin access is public, while in Java, it is package default, and there is no keyword to specifying a package default access modifier in Java. In Kotlin, a constructor can be primary. To be a primary constructor, it has to be part of the class header. You need a corresponding init block if you need any initialization routine for the primary constructor. The constructor keyword can be omitted if the primary constructor has no annotations or visibility modifiers. You can declare an object inside a class. Object is Kotlin's way of declaring singletons, just like static in Java. Notice the access similar to Java. Some category needs to be explicitly specified, as you see in the block below. My class some category dot some property. However, if the object is qualified with the companion keyword, the properties of the object can be accessed like static Java. There is no object name anymore. So when you use the object, you specify the class and the object directly. In here, you see my class, some property. Kotlin makes code more intuitive and concise. Kotlin has mapping for common operators and the required functions to be implemented to support operator overloading. For more details, you'll have to refer to the Kotlin documentation to see the complete list of mappings of functions to be overridden for each operator. Kotlin provides the ability to extend a class or an interface with new functionality without having to inherit. We have two examples of extension functions here. One is toSquareString. Function called ascending with prefix is another example. Notice the difference in syntax. In the first one is specified as a variable of type extension function. The second one is a declaration. Int is called the receiver for toSquareString function. String is called the receiver in the next. The extension functions can be called directly on the objects of the type they are extending. The number 10 is of type int, and hence toSquareString can be called directly. Similarly, ascending with prefix can be called on any string object. We already looked at delegation of properties earlier. Before we look at delegated inheritance, let's review standard inheritance again. In the following example, fruit implements iEdible. It needs to override the functions of the interface in its own implementation. In this example, a utility class edible implementation implements iEdible. Fruit can delegate its iEdible interface to the iEdible impl passed to it as a constructor parameter. Lambdas. Lambdas are code blocks enclosed in curly braces. Lambdas can be assigned to a variable. Lambdas can be passed as a parameter to a function. They are first-class citizens. When a function type is the last parameter of a function, lambda expressions can be placed after the closing parenthesis to call the function. It makes the code concise and easy to understand. We'll understand this in the example next. Let's consider the following example. An API call to some process will require a delegate object which it will call under certain conditions. The consumer of the API will implement the delegate object and pass it to the pass the object to the API call. However, if the API were to take a function as a parameter instead of an interface, the API itself would look a bit concise. Compare the inline declaration of the delegate function with respect to the interface. The function will be more concise than the interface implementation. See the comparison. Number 2. Now if the function is directly inlined, the call in the consumer will be much concise. See the comparison of blocks marked with the number 3. Compare the legacy interface delegate with the inline function in the blocks marked with number 2. The functional block on the right is more concise. As we had earlier seen, when a function is the last parameter of a function, the lambda expression can be placed after the closing parenthesis to call the function. Compare the code blocks marked with number 4. The one with the trailing lambda is more concise and intuitive. Here is a final comparison with legacy interfaces. Trailing lambda omits ceremony in the code and focuses on the operation. Now that we have covered most of the basics, we can go over our original list one by one. Concise syntax. No semicolon. That helps so we should omit semicolon wherever possible. It helps chaining expressions, eliminates temporary variables. Type inference. Here are some examples where type is inferred from the initial value. Need to specify the type is redundant. Trailing lambda. As we have seen earlier, the use of trailing lambda makes the code look more functional with very little ceremony or boilerplate. Single abstract method or SAM. Kotlin support for single abstract method eliminates the need to write boilerplate. Kotlin compiler uses the provided lambda to implement the class and its single abstract method. Data class. Here is a simple example of the user data class. The Kotlin compiler will generate the equals, hash code, toString, and copy methods. Data class have to fulfill the following requirements. The primary constructor needs to have at least one parameter. All primary construct parameters need to be marked as val or var. Data classes cannot be abstract, open, sealed, or inner. Single parameter it. It is the implicit name of a single parameter. In both the examples, the parameter is omitted in the lambda and it is used instead. For the sake of comparison, the parameter named n is used in the example 22 and is explicitly specified. When a function returns a single expression, the curly braces can be omitted and the body is specified after the equal symbol. These expressions are called single expression function. Now let's look at runtime safety. We can go over our list of runtime safety now. Let's look at the following example. The demo function accepts a parameter of type any. We check if x is of type string. If true, x is automatically cast to string. There is no need to explicitly cast x to string anymore. Let's look at the same example. The demo function accepts a parameter of type any. As question mark returns a nullable type. We will see next how Kotlin deals with nullable types with safety. Now, let's look at nullable types. Before we go into the details, let's take a slight deviation. Let's look at the following example before we get back to the runtime safety discussion. Greetings is a mutable type. Greetings type is inferred as string. Assigning nulls to a string was perfectly legal in Java. However, as we have seen earlier, string optional is a parent of string. Hence, we will see a compilation error in Kotlin. Let's browse through a few more examples. Greetings2 is a nullable string. Its initial value is high, and it's perfectly legal to assign greetings to greetings2. However, if we assign greetings2 to greetings, you'll see a compilation error because greetings2 is of nullable type and is a parent type of greetings. Let's get back to our discussion on runtime safety. In the following example, we have the variable y, which is of optional type string. In the following line, we make a call to the length of y. Looks good to me so far. However, if we compile this code snippet, we will see a compilation error as below. This happens because y is an optional string and can possibly null. We can use the question mark safe call operator to access methods or properties of nullable variables. Here is a more generic pictorial representation. You can have a nullable variable question mark and then access the property or method. Let's look at the same example. Y is type optional string. We can access the length of y using a safe call operator, which will return a null if y is null. Otherwise, call the length property. With the elvis operator, you can add a default value when the safe call operator returns null. Here 0 is the default value. Here is a general syntax of using the safe call operator and the elvis operator both together. Let's look at the assertion operator. We can use the same example. Y is a nullable string. We use the exclamation, not null assertion operator, as it is called, to access methods or properties of y, which is a nullable variable. And we do not get a compilation error. This is dangerous and should be avoided at all times. That is not using the assertion operator. Now that we have covered concise syntax and runtime safety, let's look at functional programming support. As we have seen earlier, functions are first-class citizens in Kotlin. They can be assigned to a variable, can be assigned as a value, and be used as a data type. Kotlin functions support named as well as default arguments. The need for overloading is eliminated with default values. See the different options of calling the same function. Notice the named parameters allows the arguments to be passed in any order. Higher order functions are functions that take or return functions. In this example, display speed function takes in a function called formatter as an argument. In this example, the function named provide speed formatter is a higher order function that returns a function. Scoping functions. Scoping functions are a good place for updating and applying context to objects. Apply, also, run, with, let are scoping functions. Apply, also, run, and let are extension functions. With is a standard function. In this example, the first example, shows the use of the let scoping function. Here let returns the value. In the second example, person is created using the constructor and salutation properties applied to it in the apply scoping function. The table here gives an overview of the different scoping functions. All functions except function with are extension functions. Run and let return values of the last expression, like any lambda. Functions apply and also return the receiver. Based on the desired next expression, you may choose the relevant higher order function for your needs. Here is a generic flow of choosing the right scoping function for you for your needs. You will find this on the kotlinlang.org website. We'll not go into the details of it, but this is a good reference for you. Function could be easily inlined at call sites by using the inline modifier. Inlining may cause the generated code to grow. However, if you do it in a reasonable way, that is by avoiding inlining large functions, it will pay off in performance. Any non-local return from inline function will result in returning from the calling function. That's a pitfall we have to avoid. One way of avoiding this pitfall is to use a local return with the label of the intended scope you want to return from. The only way to enforce a local return is to declare the lambda being passed with the cross inline modifier. Lambdas passed to an inline function are by default inlined. Lambdas passed with the non-inline modifier will not be inlined and will be called instead. Kotlin allows some functions to be called without using the period and brackets. These are called infix methods, and their use can result in code that looks much more like a natural language. Infix functions must meet the following three requirements. Has to be a function of class, enum, or extension, should have just one parameter, and should be prefixed with infix. In this example, you see an enum class rank and the infix function called off And the usage in the next block, you'll see Queen of Hearts as the usage of the off is used in this example. Now let's look at some declarative programming support offered by Kotlin. This is a very extensive topic. I'll just briefly uh, zip through this, and some of these topics are a matter of special discussion by themselves. Functional and logical programming support makes possible declarative programming support in Kotlin. Some examples of declarative programming in Kotlin are type-safe builders, coroutines, and sequences. Structured concurrency. Kotlin provides structured concurrency with coroutines. Important features with coroutines are suspend functions, cancellations, error handling, and declarative context switching. Additionally, flows and channel provide back pressure support and chained operations. We'll cover them briefly, however. Please refer to my other video on a detailed discussion on coroutines and flow. The suspend keyword means that the function can be blocking. It lets the Kotlin compiler help inject mechanisms called continuations to be able to free up the calling thread to do other things while the function is blocked. On the right, you see a thread not getting blocked while get token, get email IDs, and get emails are being called. They are suspend functions. Coroutines have the following parts. The coroutine body, all the lines are executed sequentially, irrespective of their thread of execution. The body is executed in the context of a coroutine scope. Coroutines are built using builders. In this example, we use the launch builder. Other builders are async and run blocking. Coroutine context can comprise of the dispatcher, a fancy name for thread pool, a name, error handler, and a job handle. In this example, the dispatcher and the job are provided. Notice the overloaded plus operator to build the context. The builder returns a handle to the coroutine, which can be used for cancellation or can be used for waiting for completion of the coroutine execution. Coroutines can context switch its operations within its body using with context. The Kotlin compiler injects a continuation into every suspend function. Here is a continuation interface which the compiler implements. It holds the coroutine context and has resume functions for happy flow and error path. The name resume suggests that it may be called multiple times, recursively or iterative, either ways. Here is a general overview of how the compiler implements the coroutine continuation, with resume calling the coroutine body, resume with exception calling the exception handler of the coroutine context. A label property to hold the state of the coroutine execution. The pseudocode on the right gives a general idea of how suspend functions are handled. The mechanism is called continuation passing style or CPS. The compiler injects the continuation object as a parameter in your suspend function. It creates a continuation object if the past object is null. Notice the recursive call to get emails from the resume of the continuation. The compiler labels each suspend function it calls, and they are called in sequence. As the state transition happens from one label to the next, the resume is called after every pass to make the state transitions. Flow implements the publisher-subscriber pattern. A flow is a type that can emit multiple values sequentially, as opposed to suspend functions that return only a single value. Flow encapsulates a producer and emits data. Consumer of flow collect the data. Here are some of the features of flow. First, it is cold start, which means flow starts emitting only after the consumer starts collecting. There's support for back pressure. Flow waits for the collected data to be processed completely before emitting the next. Context switching. Flows can be made to execute on a context desired by the consumer by using the flow on function. Error handling. Flows call the catch block provided by the consumer to report exceptions encountered in the producer. Side effect. Synchronization between side effect free. Synchronization between the consumer and the producer is handled by the flow. Collect and catch blocks provided by the consumer can be pure functions. Consider an email API which is implemented as suspend functions. It may have three functions: login, which returns a user; get email IDs, which takes in a user and returns a list of email IDs; and get email. You pass in an ID, you get an email. So let's use this as an example. We'll assume each function takes a significant amount of time, and it's already been dispatched on an IO thread pool. Then we have one more object called the view model. This is a UI element which shows the email as they are fetched. Here, the producer creates the flow using the flow function, passing it the producer block as a trailing lambda. In the producer block, calls to the suspend API are made in sequence to get each email, which finally emits the fetched email. Let's look at the consumer. Flow will not start yet until the consumer starts it by calling collect. The collected email can be dispatched to the UI component displaying the email from inside the collect block. The producer will wait for the email to be dispatched before emitting the next mail. Consumers can provide the catch block to respond to errors and provide the context for the flow to execute on. In this case, the default thread pool. Flows provide back pressure control over standard coroutine. Please refer to my other video where coroutines and flows are discussed in detail. Kotlin has support for modern types, patterns, and handling. We have already covered delegation, extension, and ranges in this discussion so far. Now let's focus our attention on how Kotlin simplifies type projections. Kotlin has in and out keywords to specify contravariance and covariance. Covariance is a means of enforcing write only, while contravariance is a means of enforcing read only. In this table, in the first row, mutable list of type string has no restrictions from the compiler. In the second row, mutable list of out string, the compiler will prevent calls which take in the string as a parameter. For mutable list of in string, compiler allows calls to add, remove, both take in strings. However, calls to get, return any, optional. Compiler Kotlin also supports star projections, wherein no read nor write operations are allowed. Here is a comprehensive list of all the features we have covered in this discussion. On the left-hand side are the general features of Kotlin. On the right-hand side, these are Kotlin features as well, mostly pertaining to classes and generics. So thank you very much for viewing this discussion. Thank you.